트래킹이 지금 존으로 돼 있어.
그러니까.
프리젠터로 방금 바꿨을 걸요.
어딨어?
내가 방금 바꿨는데.
그게 어딨지?
뭐 바꾸는 거.
네.
방금 내가 연습했.
그게 여기서 지금 프린터 되어 있는데?
트래킹 오프 아니야 지금?
맞아요.
오늘로.
Still wait for people or not? Okay, thanks for coming. Yeah, so we are pleased to have Suyun. She will give her first talk here at IDS. Thank you. And
Okay.
please.
Hello everyone. Today I will talk about how connectivity affects the extremal number of trees. This is joint work with Hong Liu and Nika Sanil. First, I will talk about our motivation. First, we will give the definition of the extremal number EXNH. It means the maximum number of edges. It means the maximum number of edges in a n-vertex graph, and G doesn't contain H as a subgraph. Here we don't need H is a induced subgraph. And for the extremal number, actually they have a fundamental theorem, Erd H Stone-Seminovic theorem. They have give this equation. And when the chromatic number of H is at least 3, actually they have determined the exactly as a multiplic of the extremal number of H. And when H is a bipartite graph, then we have Kh is equal to 2. So this one is about little o into 2. And we don't know the behavior of the extremal number of H if H is a bipartite graph. And actually, to determine the behavior of the extremal number of a bipartite graph is very hard. Even for even cycle, we don't know what's the exact number of this one. So for bipartite graph, we have some special graph is a tree. So we consider how about the tree, the extremal number of tree. Actually, Erd H and Garnet in 1959, they have given the upper bound of the extremal number of paths. And later, Fordry and Sharp, they have extended this one to all integers n. Here is also just for n is divisible by k minus 1. And the maximum value is achieved by this graph. The graph is some vertex disjoint k minus 1. If n is divisible by k minus 1, so the extremal graph is looks like this. If for every n, then they maybe have some small one. This part is the number maybe q, and n is equal to p times k minus 1 plus q. Then the extremal graph. This one is one of the extremal graph. And so this is the result for paths. So how about for an arbitrary k-vertex tree, Tk, and Erd H and s-Sós, they have given the conjecture. They guess the upper bound is also this number, n times k minus 2 over 2. And the Erd H s-Sós conjecture is still open now, and they have many results about this conjecture. Someone consider the girth of the graph is if the girth is n is 5, and then we have the exactly this conjecture is true, and someone consider the size of the tree or consider the maximum degree of the tree. And for this conjecture, the extremal graph we guess is also this graph is the disjoint union of k minus 1. So these two graphs both are not connected graph. So we wonder how about the host graph is a connected graph. So we give the definition of the connected extremal number, EXCNH. The difference between the extremal number with this one, just the host graph is a connected graph. And for this function, Caro, Patkós, and Tuza, they have given these two propositions. These two propositions is easy to check. For the first one, it means if the H is not a bipartite graph, then the connectivity condition doesn't affect these two functions. This one is because the Erd Stone seminoid theorem have given the value of this one, and so the extremal graph is about a two-rank graph, and the two-rank graph is a connected graph. So this one is easy to check. And for the second one, if H is a two-edge connected graph, then we can get these two functions is equal. So why we have this one? We can write this one in two ways. The connected extremal number of H, less or equal to the extremal number of H. We need to show these two. So if we have this one is very trivial, because if we have the lower bound of this one is also a lower bound. That is also a lower bound of this one. So how about this one? If we have an extremal graph for the extremal number of H, and we don't know if the graph is connected or not connected. If it's connected, then it's a lower bound of this one. If it's not connected, say the graph is looking like this. So we can give a copy of this one, G prime, and add an edge between these two. Because H is the two edge connected. If we add, this graph is H-free, G is H-free, and this one is also H-free. If we add a H here, because H is the two edge connected, so this graph is also H-free. So this graph, we can get a larger graph. So we can always use this one to get a low bound of this one. So this also true. So we can get these two function is equal. Now we have no, the connectivity condition doesn't affect for H is not bipartite or two edge connected. So how about H is bipartite and not two edge connected? So tree is a graph satisfying these two conditions. And actually for path, we have these two results. The first one we have shown before is the Erd H result for the extremal number of pk. And the second one is the connected extremal number for pk. Actually, I can draw the picture of these two. You don't need to see the value here. The graph looks like this. The first one, we have k minus 2 vertex here, and here is n minus k minus 2 vertex here, and choose a vertex here and connect all of this one, and this one is an independent set, and here is a complete graph, and this is a fourth graph. And for the second one, here is k minus 2 over 2. And and here is n minus k minus 2 over 2. And here maybe contain an h or not. This is dependent on k is even or odd. So these two graphs looks like this. When n is large enough, we can easily check this one is larger than this one. This one is larger than this one. And here we can know when n is large enough, this number is about n times k minus 2 over 2, and it's almost the same as that one. When, it's almost the same as that one. So these two theorem, we can say for paths, these two function is almost the same when n and k both are very large. So how about arbitrary tree? Caro, Patkós, and Tuza, they have given the definition of this one. So what this means? First, we will recall that the Erd H conjecture told us the extremal number of tk is at most n times k minus 2 over 2. And here, this is the value here is n times k minus 2 over 2. Actually, it's the upper bound of the extremal number of tk. So we want to compare the connected extremal number of tk to this number and want to find the minimum ratio between these two numbers. And actually, the gamma is always exist. This is because there is a property for dxcnh. We always have this function. If h is a subgraph of h2, then we can always find there is monotone. So the gamma is always exist. And so actually, you just remember it's just the ratio between these two functions is okay. And Caro, Patkós, and Tuza, they have get the result, get the lower bound and upper bound of gamma. And what does this theorem means? For the lower bound, it means for every tk, we can always find a graph G, and the G is tk free, and the h of G is at least 1 over 3 nk over 2. Maybe either some constant or some little n here.
Maybe minus something?
Yeah, minus something. Yeah, minus something. Minus something here is about this number. Minus something here is about this number. And here is 1 over 3. And for the upper bound, actually they have given a special tree. This tree is bk k over 3. Is a broom. What's this? This one is a broom, looks like this. Here is a path, have k over 3 or vertex here. And here is an independent set. It's k minus k over 3. So k have gave the exact value of this one. And this one is about 2 over 3 times nk over 2 is about nk over 3. So hey, get the lower bound and the upper bound. And they wonder what's the exact value of the gamma. What's the exact value of gamma? And we give the answer. Actually, gamma is 1/2. And for the lower bound, we have found for every tk, we can always find a graph G is tk free, have this many edges, is kn over 4. And for the upper bound, we found another broom. the broom is this one to change it to k over 2. K over 2. And here is about k over 2. This one is our broom, and this one is new broom. Yeah, it's different. And this one, the h is about kn over 4. Now I have told all the result of ours, and I will show our the lower bound and the upper boundaries proof. Any question now?
What is the d? K to the power dk?
Oh, actually d is k over 2. Yeah, I have made a mistake. Thank you.
It is k over 2, then
Yeah.
it's,
Because we have actually, I have give all the number of kd here for all kd.
so you mean n is at least k squared?
Yeah.
Ah.
No, k to the k square.
Yeah.
Oh, so what is d then?
Oh,
Can you write it?
actually this one is excn bkd. And n is at least k2dk. Here is d. D can choose to k
I
over
see.
2 and to
I
another
see.
number. Yeah.
K over 2.
And d is less than k plus 2. Yeah.
It's the diameter of the group.
Yeah. D is the vertex here from here to here. And any question? Okay, so I will give the proof of the lower bound. For the lower bound, we give a definition of the barycenter. So what's the barycenter means? It means for every tree, if we wanted to, for every tree, if we demeter one edge here, and we want to find a vertex V, and it always stay in the largest components. For this one, this vertex and this vertex is the barycenter. Yeah. Just remember, we always in the largest components is okay. And we will use this one to give our proof. And we also show that for every tree, there always exists a barycenter. And if there exists two barycenter, then this barycenter always is joined by an edge. And actually, for the lower bound, we want to find a graph G, and G is TK free. For every tree, we always need to find a graph G TK free and have Kn over 4Hs. So we have gave 3 kind of graphs, and they both have Kn over 4Hs. The first one is this graph. Actually, we only use this one. We only use S equal to K minus C over 4. Here C is a constant. And this graph looks like this. K minus C over 4. Here is a complete graph, and this is a complete bipartite graph. Here maybe contain one edge or not. This one is depend on this. Then K is even or odd. And this is the graph. And we can clearly can check the edge between these two is about Kn over 4, right? K minus C times N is about this number. And this is the first graph. And the second and the third graph, we call this one is SNX because it looks like a star. And for this one, it looks like some disjoint paths, so we call this PNX. And these two these two kind of graph always have Kn over 4Hs. And we will use these 3 graphs later. And now we will give the proof. Because we say we have given the definition of barycenter, and we have give the proposition said that for every tree we can always find the very center in the tree. So now we choose the very center V, and we consider the degree of V and divide the proof into 3 cases. For the first one, if the degree of V is equal to 2, so we consider a special graph Sn k minus 2 over 2. This graph looks like this. Here is an H here, and here is a k minus 2 over 2. Many vertex here is a cliff. The graph looks like this. And now we wanted to show this graph is TK free. So where is V? Because V is equal to 2. If V is here, then we should contain this part. But for this 2 part, we only have 2 times this number plus 1, and it's less than k. So it's TK free. And if V is here, because V is a very center, if we delete this H, then this part only have k minus 2 over 2 vertex is less than k half. So this vertex, every vertex in here can't be a very center vertex, so we can't be here. So this graph is TK free. This is for the degree of V is equal to 2. And for the degree of V is equal to 4, is at least 4. We consider another graph, Pn k minus 2 over 2. This graph looks like this. This is also k minus 2 over 2 vertex here, and this part also are cliffs. And here is H. And because the degree of V is at least 4, we can't be here because every vertex here, the degree is almost 3. So we should be here. If V is here, we delete this H. Every vertex here can't be a very center. So this graph is also TK free. Any question now? So we can't be embedding to every vertex here, so this graph is TK free. Now, we will show the next case when the degree of V is equal to 3. If the degree of V equal to 3, we because we want to find a graph have nk over 4 edges and is TK free. So we just suppose for every these 3 kind of graphs all contain TK as a subgraph. And for the first one, for Gn k minus c over 2, k minus c over 4, if it contains TK as a subgraph, we can get this result. That means TK counter contains a 2 spider. It means there have 2 spider. Maybe here the degree is at most 3. Maybe it's 2. And here is S1, here is S2, and the size of S1 and S2 is at least k minus c over 2. And we say that TK counter contains this structure for the first one. And using this, because we have the degree of V is equal to 3, we can draw TK looks like this. Here is V and this part. Because we have this, so for this 3 part, the components, if we remove V, this 3 part, contain at most 1 pass. So here we must contain vertex have degree at least 3, and this also at least 3. For this, it may be a path or maybe a some contain some vertex of degree at most 3, at least 3. The TK is looks like this. So this is if we have TK is a subgraph of Gn k minus c over 2 k minus c over 4.
Sorry, why there are no two paths?
What?
Why there are no two paths there?
You mean where? Because the degree of V is equal to 3. We have 3. If we remove V, we have 3 components.
Yes, and why two of them are not a path?
If they are paths, then path is a spider. We can find 2 vertex disjoint spider, and because V is very center, so this part, for every part, 2 components here, the vertex is at least k half.
Okay.
And now we consider another graph, Sn k over root 2 and Pn k root over root 2. And we want to use these three graph to get the structure of TK. For Sn k over root 2 and Pn k over root 2, the graph looks like this. Here is k over 2, k over root 2 is a cliff. Here is the path. The order of this path is k minus k over root 2. And for path, the graph is similar. And so we want to embed V in these 2 graphs. So where is V? Here we can get a simply calculation. 2 times k minus k over root 2 is at least k minus c over 2. So if V is here, or V is here, the tree looks like this. Because we know for the tree, there exists 2 vertices that have degree at least 3. So it must achieve the click here. And for this one is the same. Then these 2 paths, we can get the spider, S1 and S2. Because this one, the size of this one is at least k minus c over 2. So we can't be here. So we should be in the click. So we should be here. And if V is here, because this vertex here is less than k, so this vertex also should be in TK. So this path is also in TK. So we can find what's the TK looks like. It's like this one. V is V is here. Oh. V is here, and here we can find a path V2 to U found here. And for this vertex, because in here, for every vertex here, the degree is almost 3. So the degree of U is almost 3. So TK now looks like this one. Now we consider another graph, Sn k minus y minus 1. And y is the order of the spider. And we can always find 2 disjoint spider in this graph. This is because here is k minus y minus 1. And because the size of spider is equal to y. And if V is here, we know the order of this one is y1, and because we can always get y1 plus y is at least k minus c over 2. So if V is here, it means there have another path contain sy here. So y1 plus y against this number, we have found two spider. So V can't be here. If V is here, if V is in the clique, then we consider where is sy. Here we can always find V1 here, because we can choose longest path here, and we can always find V1, and V1 may be just equal to V. And now, because this part is k minus y minus 1, so V1 and sy may be outside of the clique, maybe in the clique. If V1 is in the clique and sy is in the clique, then this part only have k vertex, so this vertex should be in Tk. So y1 and y here, we have found two spider. And if V1 is outside, if V1 is here, if V1 is here or V1 is here, then we can also find another, we can also find two spider here. This one is sy, this one is s1. And we can also find two disjoint spider. So we can get a contradiction. So this is the proof of the lower bound. So for every Tk, we can always find a graph G with nk over 4 edges, and it's Tk free. So for the upper bound, we have proof for all the broom BKD. BKD is this one. Here is D vertex here, and here is an independent set of sets k minus d. And for this, I can show you the graph. What's the graph looks like? For the first one, GND minus 1, GND, when D is initial k plus 5 over 2, the graph is looks like this. D minus 1 over 2. Here maybe is this H when D is even or odd. And this is the first graph, it looks like this. And for the second one, what's Fn k plus 2 over 2, 1? Is a graph looks like this. They have many cliques here. And for this one, the size is k over 2. Each one is k over 2. Except one, because maybe it is not divisible by k over 2. For this one is Fn k plus 2 over 2, 1. For the third one, for FND2, this one, because D is equal to k plus 3 over 2, so this is also clique. One is k plus 1 over 2, and the other is k minus 1 over 2, k minus 1 over 2, and except 1. This is FND2, and for FND3 is a graph. These three graphs will have all share a common vertex here. And for this part, it also some clique, but for this, it denotes a perfect matching here. And here, the size of this one is also k plus 1 over 2. And here is k minus 1 over 2. L is also a clique, and this one is linear matching, and the K is odd. And for D is at most K plus 1 over 2. Actually, it's almost a K minus D regular graph. So this is all the graph for the connected extremal number of BKD. Any question?
So these are all unique extremal graphs. So when you have equality, you most of this. So when you say these are tight examples,
Yeah,
do you mean that there's no other example, or
yeah.
I see?
But this is for n is at least K2 dk, because we have give a graph here. They have a small graph. We have this one is a small graph, right? We didn't consider this one. Actually, this one is also a graph for this. But when n is large enough, the h is less than this one, so we didn't consider this one. So this is all the graph here when n is large. And now, actually, what's the exact number? The value of this one actually is about n half times d or k minus d is about this one. Is the connected extremal number of BKD is about this. Maybe either a little O here. It's this one. So for when we choose D equal to K half, we get the upper bound. And now I will show you the proof of this one. We can quickly prove this. First, we consider G is a BKD-free connected graph with n vertex, and we choose a vertex V, and the degree of V is the maximum degree. And we will divide the proof into 3 cases. For the first one, it's very easy to check. The maximum degree is bounded, is almost K minus D, and we can easily get the h of G is this number, K minus D times n over 2. And for case 2, because delta G is at most K minus 2 and at least K minus D plus 1. So because we have n is at least K2D times K, so we can easily find Bruce the first search tree from V. It looks like this. First, we have the vertex V, and we choose its neighbor. Here is V, the first layer, and we choose the neighbor of V, and then choose the second neighbor. And using this way, because n is at least K2D times K, so we can find a path from V here. The length, the order of this path is at least dk, so we can find a path looks like this. And use the Hinge-Hall principle, we can find a subpath here. We can find a subpath here. From here to here, we only have one neighbor here. And because we know we have many neighbors here, so the red one is BKD. And it's a contradiction because we say the graph is BKD free. And it's the case 2. Any question? This one we can find a path. And for this path, there is no neighbor of V, only this vertex. So from here to here, and either other neighbor of V, we can find our BKD. And further, and for case 3, we know the maximum degree is at least k minus 1. It means the degree of V is also at least k minus 1. So we can get a observation. That means the circumference of G is at most d minus 1. We can show here. Because why we use CG to means to denote the circumference of G, and then it means it's d minus 1. It's almost d minus 1. Why? If near can turn a cycle at least d, the order of this one is at least d. V may be here or V may be here. Near can turn a path from V to this one. Because G is a connected graph. Then and we know V have many neighbor because the neighbor of V is d k minus 1. So we can find the dkd here. From here, maybe from here to here is dkd. So we can get this one, the first observation. There is the circumference of G. The upper bound is d minus 1. Then we use the result of Koplov because they have considered for two connected graph and the conference is at most k almost k minus 1. They have given the upper bound, and actually for this one is the edge of this one. We can change k to d here. So actually this is gnd d minus 1 over 2 is what we have definition. Then for if G is two connected, then we can just use this theorem to get the upper bound. So now we consider G is not two connected. And because if G is not two connected and G is connected, so we can say there have many blocks of G, and we write it G1 to GS, and the graph looks like this. Here is G1 and GS, G2, G3, maybe something like this. G4 to GS. Something looks like this. And because for every GI is two connected, so we can also use the theorem of Koplov to get the upper bound of the H here for every GI. And now we can use the result of Woodall to get the lower bound of the circumference of G. Here, because they have given this result. And if D is here is K. If K is equal to D minus 2, then we can get the bound is about EXN. D minus 2 is about N times D minus 3 over 2. We can also get the upper bound here. So from the result of Woodall, we can get the lower bound of the circumference of G is at least D minus 2. So the circumference of G is either D minus 2 or D minus 1. And because and we will use these two, and G is BKD free to get and this one, every edge here is the edge here is bounded to get the upper bound. And because we don't have much time, so I didn't give the detailed proof here. And then, so this is our proof of the upper bound. Now I will talk something about the open problems. For the first one, because we have draw many picture, many graph here, and so what which parameter of the tree determine the asymptotic behavior of the connected extremal of the tree. And actually, we have given some regular graph here. So for the first one is the maximum degree of t. For every maximum degree of t, we can always get a lower bound, use the delta t minus 1 regular graph. Is tk free. Consider the maximum degree of t. So we use the delta t minus 1 regular graph. Is a lower bound. Is the tk free, this one. This is first one. And for the second one, what is the size of the smaller color class of the bipartial of t. It means because t is a bipartite graph, we can draw the graph looks like this. Here have some h here. It's not complete. This is the tk. And so we assume this part is a smaller one. Maybe we say this one, the number here is capital A, and this one is capital B. And so if we draw a graph, it's this one. This is A minus 1, and this is N minus A minus 1. So this graph is tk free. Actually, this graph is, maybe here we have one edge here. This graph is Gn k minus 1 over 2 is this graph. So this one is the second one. And so actually, we have draw some other graph. Is not this one. We have given snx and pnx is different to these two parameter. So actually, these two parameter alone doesn't suffice to determine the connected extremal number of t. For example, we can give the barrier tree. So for the barrier tree, we have 2 times r minus 1 vertex. The barrier tree looks like this. Here is, and we have many layers, and the smaller one looks like this. If r is equal to 3, is this graph, right? And for the barrier tree, if we consider the maximum degree, because the maximum degree is equal to 3, so we can only consider 2 regular graphs, and it only have n edges. If we consider the smaller color class, so it's about 2 times 2r minus 1 over 3 minus 1. The smaller color class, the number is this one. So we can use the graph here. A minus 1. A minus 1 means this 1 minus 1. So the graph is this. 2r minus 1 over 3 minus 1. How many edges of this one? It's about this number times n. So it's about this edges. But actually, we can give another graph. It looks like the snx. The graph looks like. The graph is this one. It's the snx type. Here, the length of the path is 2, and here are some cliques. And the size of this is 2r minus 7. And because we can't embed the v here, v should be here. And the graph looks like this. We consider vertex here, and maybe some vertex here. And because the barrier path in this graph is at most 2, and this graph is the barrier tree free. So we can get This one is a very free graph, and the h is about 2 times 2r minus 7 minus 8 over 2 times n over 2r minus 6 or maybe 5, and it is almost n times 2r over 2 is about these edges. So we can say the edges here is larger than these two. So we can say these two parameter doesn't suffice to determine the connected extremal number of tree, but actually we don't know what's the third one, and we guess maybe the SNX type graph and the PNX type graph maybe help to find this parameter. And this is the first problem. And for the second one, Caro, Patkós, and Tuza, they have considered the monotone of the graph. Actually, if the graph is a pk, we can say if pk, we can say when n is small, we can say it's not monotone. We can say here, we consider kpk, the graph is here. It looks like this. Here we have k minus 2 vertex and it's a clique. And then they have 2 vertex outside and they have a common neighbor here. For this graph, it's pk free. And if we consider another one, n is equal to k minus 1, because it only have k minus 1 vertex. The k minus 1, the graph doesn't contain pk, and the h of this one is less than this one. So when actually we didn't find a better example for this one, to choose another one such that n is larger than k, we didn't find a better example, just this example to show when n is small, is not monotone. So they wonder, how about n is large, there is a connected extremal number is monotone. And we have shown that when h containing a cycle actually is monotone. But if h is not containing a cycle, we don't know. So how about if h is a tree? Yeah. Next word. Thank you.
Thank you. Any questions?
You can ask a question. So can you go back to fourth slide, please? So you.
Which one?
Fourth slide, like
Page
four line. So there was some statement: if chromatic number is at least 3, then
Page 4.
yeah, page 4. Yeah, the first.
Yeah.
No. Next one. Yeah, the first two.
Which one?
4.
4. Okay. Okay.
So the first statement, when chromatic number is at least 3, there is this 1 plus small of 1 factor. I would guess that it
You
should be
mean
just
here?
equality, right?
You mean this one?
Yeah, the first one. I would guess that it should be just equal. Like, do you know an
Yeah.
example when they are not equal? or is there
Actually, I guess it's equal, but but I don't know. It's they give the proposition and then they didn't give the proof. And actually, we think it should be equal and don't contain the little hair.
Okay.
Yeah.
Oh.
I couldn't prove it today in 10 minutes.
You solved it?
I couldn't.
Any question?
For the last one of the first open problem, I was wondering whether it makes sense to consider this parameter that you use this fact that every tree has berry center, right?
Yeah.
And so when you delete the berry center, you split the tree into various components,
Yeah.
different
Some
sizes, right?
components. Yeah.
So if these components have if you have many components
Yeah.
of small size, or if you
Actually.
have one component with a big size,
Actually, this is very right, and because every when if we guess we have 4 or more degree, right?
Yeah.
And here are some components. If we delete V, then here are components, right? Yeah. And actually for every this one except one, the size of this one is at least k/2 because we can delete H here. If we delete H, they should be the largest components. So for every this one is at least k/2. So for every one, the size is at most k/2. Yeah. For every components, the size is at most k/2. And yeah,
So
this is the definition of the barycenter.
yeah. I was wondering whether you can use this kind of structure to measure some. I mean,
Actually, the graph SNX tab and P SNX tab and PNX tab actually is used the barycenter. Yeah, because for the graph, this one, here we sometimes we choose this part is less than k/2, so V should be here, and V is barycenter here. And we can always and we can also choose some size such that this part is less than k/2, so V should be here. And so these two graphs is used the barycenter to construct. Yeah.
yeah.
So we think maybe this graph, yeah, maybe helps to find the parameter.
I have another question. So the cases that we don't know the extremal number for connected graph is when graph is bipartite and has
Yeah.
cut edges, right?
Yeah.
So does it make sense to consider like not only trees but the maybe trees of even cycles where you replace vertices of tree by C4 or C6 so that those graphs are not those graphs are still bipartite and yet
Yeah.
has a lot of cut edges. So
Yeah. But for cycle, the extreme number we don't know. For even cycle.
oh right.
Yeah.
For even cycle we said.
Yeah.
I see.
And actually, last time Morris have gave another problem because our result, we give the lower bound. We give the lower bound here is kn/4 and minus something, and here is kn/4. Maybe just minus or add some edges. And he asked if we can find a special tree just equal to the minimum number of this one. Yeah, because maybe this graph is not the minimum to achieve this connected extreme number of tree. Yeah, so he said maybe if you can find a graph just equal to the minimum, maybe. Yeah, but we didn't get. And Nika said maybe the graph looks like this. Hey, wonder some graphs looks like this. Yeah, some complex the graph. Yeah, maybe have something like this. Yeah. And any question?
Any more questions? If not, let's thank the speakers. So we finished at 5:29.